Okay, I guess I am gonna get started now. Just to go. First of all, are there any questions about anything technically or logistically? Anything from last time about graphs? Okay, breadth first search, data structures for graphs, or about any homeworks or anything like that? Any questions? Okay, what I think I'd like to start off with, last class we were talking about breadth first search. I was talking, again, what was breadth first search? It was a systematic way of walking over the graph, okay, where we visited every edge and every node in a prescribed way. And there's a lot of applications of breadth first search. Once you, and they all basically work by programming the stubs that were left in the breadth first search function to say, do something when you visit the vertex for the first time, or do something when you visit the edge for the first time. And a classic example of breadth first search in action is basically two coloring a graph. So we say that a graph is bipartite if, let's say a graph, let me try to think. A graph is bipartite if there are, the vertices can be partitioned into two colors such that all edges cross from one color to the other side. So we're going to say that there's left colored vertices, which I'm going to make orange. And there's right colored vertices, which I'm making green. And so long as every edge touches two colors, okay, different colors, then we say the graph is bipartite. And two coloring is the problem of, what you call it, the problem of trying to color the vertices so that every edge, the two endpoints are of different colors. Bipartite graphs are very important because they arise in many applications. An example might be the graph that we have of students and the courses they're registered for. You have, on one sense, you have courses. On one sense, you have students. Certain students are registered for some courses. Every course has students in it. There is never a student registered in another student or a course registered in another course. So this is a bipartite graph. And bipartite graphs are very simple, okay? There's certain algorithms that work very nicely on bipartite graphs. And knowing whether your graph is bipartite is kind of an important thing. So how can we go and find if a graph is bipartite, given the graph? Well, basically what we're going to do is do a traversal, a BFS, where we notice that when we start from the first vertex, if we make it green, what do we know about any of its neighbors? If we have a choice of green and orange colored, what color must any neighbor of the root green vertex be? What color must they be?
Orange.
Orange. And likewise, any orange vertex, what color, if we have an edge in the course of our breadth first search between two vertices like that, that would say, we've got a problem, right? Because now we've got an edge between two colored, what you call it, two vertices that were both colored, orange. What do we know about the child of any node? Again, in a breadth first search, we are going to be discovering new vertices. What do we know about the color of any vertex that gets discovered? What color should that vertex be? Green. In general, the rule is it should be a different color than its parent, right? So if you're white, your parent is, if it's white and black, a white kid has a black parent, and so on. Okay. So what is the idea of an algorithm for doing two coloring a graph? Well, let's take a look at it. First, we'll say every vertex has a color, and initially they are uncolored. Initially, until we get a contradiction, every graph is bipartite graph. The graph is bipartite. We're now going to initialize our breadth first search, okay? And basically for every vertex from 1 to n, we're now going to ask ourselves, if the ith vertex is not discovered, then that means we should do a breadth first search from it. So this is going to try to color every component of the graph. And basically the first vertex we're going to say is white. We're going to do the component will be white. We'll do a breadth first search. We need to do something on every, whenever we see an edge. Okay. If we have an edge x, y, and the color of x is the same as the color of y, then we're in trouble. Every coloring we did was forced. This can't be bipartite, and we go back and we complain and bomb out. Otherwise, vertex y is going to be the same color, the opposite color of x. Okay, any questions? And what does the complement function? Well, basically it just generates the opposite. If the color is white, we're going to get it as black. If it's black, we're going to get it as colored white. Okay, and in general, if it's uncolored, we will return it as uncolored. Any questions about that? Okay. So this I claim, notice how, again, we're doing, in this case, we're doing this on every process at time we process an edge, okay? We could have perhaps colored the vertex when we discovered it. That would have been done in a process vertex. Any questions about how we would use this breadth first search idea to two-color graphs? What is the running time of this algorithm to two-color a graph? If I have a graph with n vertices and m edges, what's the time it's going to take to two-color the graph? Somebody.
N plus m.
N plus m. Why is it n plus m? It's n plus m because we're doing a breadth first search. Whenever we visit an edge, we're going to do this. What is this work? This is a constant amount of work. Does everybody see that? We'll do a constant amount of work every time we visit an edge. It doesn't look like I'm doing anything when I process a vertex. That's a constant amount of work. The total time is going to be n plus m. Any questions? This is what BFS algorithms look like for graphs. Any questions? Going once, twice. Okay, sold. Okay, what I'd like to now do is get to the problem of the day. Today we're going to talk about go beyond breadth first search and go to other proposals. But first, the daily problem is about breadth first search. What is the question? It says that we are doing a breadth first search. What do we know about every edge in the graph? Okay, the claim is that if we did a breadth first search on a graph that's undirected, every edge is either a tree or a cross edge, and see what that means. And what is a cross edge? It means an edge to a vertex where x, y, where y is neither an ancestor or a descendant. Okay, so let's try to think what that means. Let's imagine a breadth first search tree growing. Do we see, ooh, look, we discovered somebody, we discovered somebody, we discovered somebody. Is it possible that, let's say at this point, I have an edge that is going to go from here to here. So let's just think about what I'm trying to do. Then this is kind of the important point. What breadth first search and, as we will see, depth first search do is they order the, they assign kind of directions to the edge based on who was the first discoverer of this edge. This vertex, the root, discovered these edges. Then when we processed this vertex, it's possible we discover a new vertex. Does everybody see it's also possible that I have an edge that goes to one of my brothers? Okay? That as I go through my neighborhood here, the first time we visit this edge, I find it's an edge to my brother. Is it possible I have an edge that goes to a, a neighboring, a younger brother, an older brother? Let's think about this. The directions are coming when I'm expanding the edges, when I first visit the edges. When I process,
no, because that,
I could have found that, I could have done that. Is it possible that the first time this edge over here was encountered was when I processed this vertex? I think I heard someone say no. Is that right?
well, it depends on on what order you process the nodes in, but if you go from left to right, I would say no, because you would have already processed the older brother.
This is the key point here, so I want you to listen. I could not, assuming I'm processing the vertices from left to right, that's sort of going to be my convention. Then when I looked at this, when I went through all the outgoing edges, if there was an edge from 3 to 4, I would have discovered it when I was processing 3, not when I was processing vertex 4. Does everybody kind of see that? So there is some constraint on what the shape of this tree is. I can have edges from me to younger siblings, but I can't have an edge from me to an older siblings in terms of discovery, right? Again, a tree edge is one of these purple edges that where I go to a descendant. A cross edge is where I go to a node that is neither an ancestor or a descendant. Let's continue this process. When I now look at processing 5, could I have an edge that goes from 5 back to 1 if I'm doing a breadth first search?
If it's undirected, no.
It's undirected, no. Why not?
Because then 5 should have been a child of 1 when
5 would have been a child of 1. Does everybody kind of see that? The breadth first search, because of how we're doing it, puts certain constraints on things. Okay? Can I have a back edge that goes up like this? Okay? I'm going to claim the answer is no, because if I could, that would have made 5 an immediate descendant of 1. Any question? The discoverer of 5 would not have been 2, it would have been 1.
Professor, what happens if we also have an edge between 3 and 5? In addition to 2 and 5. What happens if we have an
edge from 3 to 5? Is that legal? Well, when I expanded 3, 5 had already been discovered. I'm the second person to discover 5. That's a little bit like being the second guy to invent the telephone. It's not as good. Okay? But I could not have had an edge that went upward like this. Does everybody see that it could not have been 5? The edge 3, 5, I would have discovered when I explored 3. There is a
so I get that. I'm just wondering because it's not a cross edge, clearly. But it's also not a tree edge because it doesn't form a tree.
Okay,
3,
so
5.
what do I want to claim? Well, I'll be a little bit more precise about the edge types when we talk about depth first search, okay? But I want to kind of see that it should be clear a tree edge are the ones that were involved in the discovery of new nodes.
Okay, so we're not talking about literally like a tree
No, it's not a tree.
drawing from the,
One
okay,
thing that's
gotcha.
interesting, though, is that breadth first search along the way finds a subset of your edges of your graph that form a tree. Whenever you have a node, the parent relation, right? When I discover you, I become your parent, right? That parent relation is going to define the tree, okay? A tree of discovery, okay? But there's other edges in the graph. But in a breadth first search, we're never going to go on an undirected graph. We are never going to go back to a higher ancestor, because if we did, we would have discovered this node when we processed the ancestor. So that's a no-no. We can't have an edge that goes from me to a non-descendant on a higher level, because if so, I would have first discovered this edge when I processed the older guy. So that's a no-no, okay? I can have edges that go to previous nodes on my level, and they can go to nodes on a lower level, okay? But they can't go 2 levels down. Why do we know they can't be a node from here, an edge from here to here? Because again, if it skips this level, it would have, when I processed this vertex, discovered that vertex. So I want to claim that that it should be clear that there are these restrictions on what edges can do in a breadth first search. It kind of lays out the edges in the graph in a way that gives me a tree, but also has other constraints on what it does with the edges. Any questions?
Yeah, can you explain again? I'm sorry, can you explain again why you can't go 2 levels down from like an upper node to a lower one?
Now let's think about it. Bunk, 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 bunk. I'm doing my breadth first search of discovery, right? Here is a node that's going to be 2 levels down. Now notice that if I had an edge between these two, this would have been the parent of this, right? So it couldn't look like this because we were expanding the vertices in the order of creation. I worked through all the descendants of this. There is no way that I could discover that, I'm not going to get a chance to this one up here will discover the edge when we process that vertex. Okay? So it couldn't have been discovered 2 nodes down. What could have happened would have been bunk. Let's call this thing 1, 2, 3. Okay? Let's call this one A. Okay? What would happen? I would do 1, I'd process it. 1, 2, let's call it 2, 3, 4. 2, I would process my 2 children. 3, I would now, discover A. And later, when I processed this node over here, I would also discover a node to A that had been previously discovered, right? I would discover that edge when this guy got processed. So that's why I can't jump 2 levels. The tree won't have those 2 levels.
Oh, so you're saying that if you have like an arrow from one node to another, that means that it had to have led directly from that node to the next one, but like, didn't you say earlier that it has to be like the parent node in order to have like a directed edge to the other edge?
No, okay, direction here is I'm going to say first guy to process it. Does everybody agree in an unlabeled edge? Here's an undirected edge. That's an edge. In the course of a traversal, I will either visit it from this node and be the first one to walk down this edge. This vertex may have been discovered or may not have been. But either I go from this and first look down this edge, or I go from here and first look down that edge. The direction that I'm assigning is basically what is the order of the first look on the edge.
Oh, okay. Got it.
Okay? Fair enough. Any questions about this? It should be clear that these breadth first search organizes the tree, and this is going to be even more important when we start talking about depth first search in a minute. Any questions? VFS. Okay, depth first search, remember, again, what was breadth first search or depth first search? We had a, we were going to color each vertex. Is going to go from a stage where it's going to go from undiscovered to discovered to completely processed. That's kind of the evolution of each vertex. Breadth first search, we also had a data structure of vertices we haven't finished processing yet. For BFS, this was a queue. For DFS, it's going to be a stack. On one level, the only difference between a breadth first search and a depth first search is that instead of storing our intermediate vertices in a queue, we're going to store them in a stack, okay? A last in, first out stack, okay? Well, actually, wait. First in, first out is a queue, right? Last in, first out is a stack, okay? Any questions? So you could have implement depth first search just by implementing breadth first search the way that we did before and use a queue instead of a stack instead of a queue. But in fact, with breadth first search, it's actually kind of nice to implement it as a recursive algorithm in a way that eliminates the need for a stack. Hopefully you guys know that how recursion is implemented in a programming language. Basically, there is a stack of records that is maintained by the runtime system of the programming language. So recursive calls are really things on a stack. And depth first search is basically going to do it as I'm going to show you a recursive way of doing it. What do we know? Depth first search for a vertex. What are we going to do? We're going to do a depth first search given a graph and given a vertex V. What are we going to do? Well, in addition to what we maintained before, we are going to maintain what I'm going to call the discovery and the entry and exit times, okay, of every vertex, okay? So there's a what time is things happening. But what is the flow of this thing? We do a depth first search starting from V. That means we're going to mark V as discovered because we're going to search for it. Now, just like breadth first search, we're going to loop through all the outgoing edges from vertex V, okay? And so long as that is not null, meaning there is an outgrowing edge, let's consider the edge V comma Y. If Y was not discovered, then we discovered it. And so if there was an edge which we looked at from V to Y, the discoverer of vertex Y is V. Does everybody agree with that? And I now have a chance to process that edge. But what I'm going to do is start immediately doing my depth first search now. Remember, depth first search from a stack meant that we were doing last in, first out. The moment we discover a new vertex, we're going to interrupt what we're doing and start exploring down from that. Okay? And then, with a little bit of logic to make sure I don't visit the edge twice, basically, test whether or not I am the first, time I'm visiting this edge, and if so, that's it. Okay? So the difference here between breadth first search and depth first search is that I'm going to start immediately doing a depth first search from the new vertex I discover. Explore all the consequences to that before working back. Any questions? Okay. Let's look at an example. Okay, before I give you too many weasel words. What is going to happen on a depth first search from vertex 1? Again, I got to maintain a stack for every vertex, right? Well, first of all, for every vertex from 1, 2, 3, 4, 5, 6, 7, 8, I have a state for it. And I'm going to maintain a stack of stuff to do. Originally, if I'm doing a search from vertex 1, what's going to be on the stack? Vertex 1, and vertex 1 is discovered. Right? Now, what am I going to do? Start a depth first search from vertex 1. What does that mean? I'm going to go through my outgoing edges, and the first edge I have is edge to 2. 2 is a newly discovered vertex. I am now going to push 2 on my, let's say I was in stack 1, state 1. I now discover a new vertex. Now I'm going to be in vertex 2. Vertex 2 is discovered. Okay? And so I have added this edge to my depth first search tree. Now I'm going to stop where I was on 1 and start working on 2. Look at 2. What are my outward choices? 2's neighbor is 3. And that's a new discovery. I'm going to put 3 on my stack. And I have discovered number 2, 3. From 3, I look at the outgoing edge, and son of a gun, I have discovered a new vertex, number 4. That's great. More discovery. This has been discovered. This has been discovered. From 4, I look at my neighbors. 3, well, 3's already been discovered, so I don't care about it. 4, 5, well, 5 is a newly discovered vertex. Bingo. I'm now on 5. Now from 5, where are my outgoing edges? I could go to 3. Well, from 5 to 3, yes, that's a new edge. Or 5 to 2, so I could go from 5 to 2. 5 to 2 is something. That is a back edge. That goes back to an ancestor of me. Then after 5 to 3, that is an ancestor. Then 6, oh boy, I discovered a new vertex, 6. And now I'm going to do my search here. But from 6, what do I know? There's no other outgoing edge. The only edge is to 5, and that's already been discovered. So what am I going to do? I look at all my neighbors from 6, I'm done. This is now completely processed. I get 6 off my stack. Where do I go next? I go to 5. 5, what do I know? I've looked at all of my outgoing edges from 5. Okay. 5, actually the 2, I went that way and I went that way. From 5, I've looked at all my outgoing edges. I'm done. 5 now is completely processed. I go back to 4. 4's outgoing edges, all of them I've been looking at. 4 is now completely processed. Okay. I get up to 3. I look at all of 3's outgoing edges. They're done. 3 is completely processed. Does everybody see that I discovered? Okay, no, that's not good. Discovered. discovered, discovered, finished, went back, 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 okay? There's kind of this nesting that's happening when I do this, and that's quite fine. So what is it? 3, I explored. 3, I'm done. 2, now I look at the neighborhood and I have another vertex I have not yet explored. So congratulate me, I have just discovered vertex 7. 7 goes on the stop. Are there any other consequences from 7? I visit vertex, from 7 back to 1, that's the back edge here, okay? From 7 to 2, I've already done that edge. I'm now finished with 7. 7 was discovered and now processed. And now I'm back at vertex 2, and there's nothing else for me to look at, so this is processed. And I go back to 1, and the only thing I haven't visited is 8. Yes, I have discovered 8. It has been discovered. I look around it. I don't see any other new edges out of it. I back up. This is now processed. 2, I had to finish before I was from 1. I now look around. Everything's been completely processed. And I pop it and I'm done. That is what a depth-first search looks like. Any questions about that? Okay. Any questions about the mechanics of how you do a depth-first search on a graph?
I had a question. When you're doing a traversal, like a DFS traversal, is there sort of like a different implementation where when you're traversing through it, you can't necessarily go back from 5 to 2 because that's a parent node. So instead you have to end up going from 5 to 6?
No, your basic rules are, if you look at the code that we were doing this, what is happening in the code? You are in some loop here. Unfortunately, the break was a little undesirable. What was the loop? While we're going through all the outgoing nodes of vertex 2, okay, V, let's say V was 2. We look at all the outgoing edges one by one. If we discover a new vertex, then we immediately do a depth-first search from that vertex. Once it has explored everything that we can, okay, then we eventually come back here and look at the remaining neighbors of vertex 2. Okay? So again, think of what's happening in a BFS. What's kind of happening on a BFS is you're starting at one place and you're exploring the neighbors. You're exploring them in terms of age. This is the kind of thing that's going to be happening in a breadth-first search. In a depth-first search, you're starting at one vertex. And you're saying, ooh, I discovered somebody. I discovered somebody else. I'm desperate to try to, maybe I have some edge going back. I discovered somebody new. I have an edge going back. Edge going back. Ooh, discovered somebody new. Okay? In a depth-first search tree, you're trying to discover things as quickly as possible rather than radiating out from something. Any questions? Okay. What difference does it make? This probably does not sound exciting. Okay? The interesting thing is that, again, when we think about the edge classifications of DFS, certainly there's going to be tree edges. Some edges will be trees because they discover new vertices. Some edges will be back edges, meaning they go to an ancestor. Notice this edge, if I just first walked on this edge when I process this guy, I go back to my grandparent, okay? An edge that goes back to an ancestor is called a back edge. You could also imagine an edge going from a node to its grandchild. That's skipping more than one generation. Skipping one node to your child, that's a tree edge. A forward edge skips more than one generation down. A cross edge goes to somebody who's not, it may be a brother, but they're not an ancestor or a descendant. Any question? Every edge, there's only these 4 possibilities. But what's interesting is, and the key point is that if I have a directed, I do a DFS on an undirected graph, every edge is either going to be a tree edge, either it discovered somebody, or it goes to an ancestor. If it goes to an ancestor, it is a back edge, okay? If it discovers somebody, it is a tree edge. The interesting thing is that in a depth first search on an undirected graph, you can never have a forward edge that goes to your grandchild. Why not? Is it possible that you have an edge that goes to your grandchild?
So
Don't hear you.
So in the case of like the one with 1, 2, 3, if you had like that one, then if it was a valid depth first search, then you wouldn't have the edge between 1 and 2, since you would
Exactly
continue
right.
down
I
to
went to
3.
1. The moment I discovered 2, I'm out of there, right? And when I then discover 3, I'm gonna process it, and the edge would be oriented that way. Because once I left this guy, I didn't get back to it until I had cleaned my stack out, right? So I can't have that kind of forward edge. No forward edge. Could I have an edge that would go to somebody who's not a relative of mine? Like, not a thing like this. Is it possible I have an edge that goes to a cross edge to somebody who is not my ancestor or descendant? No, because if there was an edge between this thing, when I processed this vertex, I would have discovered this guy. And that's how the thing would have looked. Okay? So the amazing thing that turns out to be very, very useful is that a depth first search organizes the edges of the graph in such a way that there is a tree of discovery. Every vertex gets discovered, and every other edge, okay, goes from a vertex to an ancestor. Either it discovers somebody new or it goes to an ancestor. That is kind of the organization that the depth first search does. Any questions about that? You may say, well, what's so exciting about it? But does everybody get this idea of what the organization of the edges is? That kind of what you do a depth first search of any undirected graph from any vertex. Every vertex is going to get discovered, assuming it's connected, and every other edge is going to go back to an ancestor. Okay, and depth first search does that organization. Any questions? Okay. This organization has some interesting consequences. Okay, and powers a lot of different algorithms on using depth first search. For example, suppose I want to find a cycle in a graph. You guys know what a cycle is. Let's say I've got this, and here's a graph. See if I can do it. Boom. Uh-oh, what's wrong with me? Here I've got me a graph. Here I've got some edges. What is a cycle in a graph? A cycle is a walk where I get back to where I started from. Does everybody see that if a graph is not a tree, it has a cycle? how can I find a cycle in a graph efficiently? I have a graph. I might want to find if there is a cycle in it. How can I do it? Well, let's say I do a depth first search. Bang. Ooh, discovered somebody, discovered somebody, discovered somebody, got trapped, went back here, discovered somebody, went back here, discovered somebody, went and had a back edge. Does everybody see a back edge is one that goes to an ancestor? The moment I have a back edge, do I know that I have a cycle? The answer is yes. I've got a path, a tree, it got me to this point. If the edge goes back to the ancestor, the path from me in the tree to my ancestor, kabunk, kabunk, okay, kabunk, 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 plus this new edge has to be a cycle, okay? So basically, what do I do if I want to find a cycle in a graph? I start doing a depth first search, okay? And when if I ever have an edge where, when I'm first processing the edge, the parent of this edge, if I discover a new vertex, it doesn't matter. If I have an edge, if the parent of this vertex, okay, if I have an edge x, y, if the parent of y is not x, okay, so if let's just make sure I understand it. Suppose I am processing an edge that goes from x to y, okay. Actually, let me just double check this for a second. If the parent, okay, hold on. This looks a little backwards. That's why I'm a little scary here. It's basically the case. It should be clear that if I have I have to make sure I get the orientations of these things right. If I have an edge where the parent of me, if I have this vertex, that edge that goes from y to x. I'm still going to say if this is y and this is x. If the parent of y is not x, then that is a back edge, okay? And if that is true, then then I have found a cycle. Basically, the path from y, from x to y in the tree, plus this back edge, is going to be, give me my cycle. Any questions about that? The labeling you have to look at a little bit. I'm a little bit funny about how I called this now. But the concept should be clear in the drawing, okay? That if I go to somebody, if I have an edge that goes back to somebody that's not my ancestor, the first time I process it, well, it's a back edge, and the back edge plus the tree path is enough to reconstruct the edge cycle. Any questions? Okay, here's the hard question. What is the running time of an algorithm to find a cycle in an n vertex m edge graph? Suppose I want to find a cycle in it. How much time will that algorithm take? Somebody.
Wouldn't it just be the same runtime as depth first search? Because eventually, like somewhere in the middle of that, if you have a back edge, then you know that it's a cycle.
The truth is that whenever I get my first back edge, I will stop. And you're saying that if I did my traversal, if there's going to be a cycle, when I go back and do it over every, if I went back and did it over every edge, okay, every edge is either a tree edge or a back edge. By the time I've walked through all the edges, I know which one is a back edge. You're saying that when I look at m edges, I will have found a cycle by the mth edge and maybe before. Okay, that's why you're saying it's n plus m. And I agree. But what if m is very, very large? Suppose I have an n vertex graph. What is the longest amount of time until I will find a back edge? How many edges can I look at till I get a back edge?
M over 2.
Say m over 2. I'm going to claim it's n. Why is that? Every edge, if it's not a back edge, is a tree edge and discovered somebody, right? Look, I discovered somebody. I discovered somebody. I discovered somebody. How many, if there's n vertices, how many discoveries can you make of new vertices? How many? N minus, well, let's say the first vertex you're kind of given, so kind of the discovery counts for free, but you will discover at most n minus 1 other vertices. Each one of these will use at most one edge. Then by the nth vertex edge, you will find a back edge. That's because a tree can only have n minus 1 edges in it. Okay, so the interesting thing is you can find a edge, you can find a cycle in any graph on n vertices and m edges in order n time for any graph. Any questions? So finding a cycle is a good thing to be able to do. It's kind of a kind of basic step in a lot of different algorithms. Any questions? Okay. Any questions about depth first search and how it orders things? Okay, I'd like to go through two more advanced algorithms now that rely on depth first search as the thing that makes it go. And when it comes to understanding these algorithms, part of it, again, I strongly look at what you call it. I strongly encourage you to read through the book carefully. Look at the code to understand how and why this is working. But I want to, again, depth first search and breadth first search basically work by visiting all the vertices and edges. The edges get labeled in a particular way, okay, so that the structure makes things easy and obvious, okay? Now, when it comes to these more advanced graph algorithms, one thing I want you to do is to try to understand the algorithm and how depth first search did its magic. But even more important is to understand why the problem is important. So one thing that I find in graph algorithms, designing new graph algorithms, really new graph algorithms, is a very hard thing. What I find is that there's a small number of graph problems that once you know algorithms for them, a lot of other applications turn out to really be the classical graph algorithm problem, maybe in disguise, okay? And so, so I want you to know about what the problem is of finding articulation vertices, not only because I'm going to show you an algorithm, but realize that once you know what the problem is and what the, that there is an algorithm, you can pull that out when you need it. So, okay, articulation vertices have to do with finding the weak spot in a network, okay? Now, suppose you are a terrorist and you want to attack this graph, this phone network. What is the right vertex to try to blow up if you want to attack or disconnect that network? Which vertex is it? I'm seeing red.
The green?
Well, green, what happens if you blow up one of these green vertices? Anything at that node is going to be not happy. But notice that nobody else really misses the green node. They're still all connected, right? What if I blow up this green node now? That's not going to hurt anyone. Once this was done, however, if I blew up both these nodes, what happened if I blew up that node? Does everybody see that now this guy has been disconnected from the graph? There is a non-blown up node that would now be severed from the graph. It used to be one component. Now it is two connected components. An articulation vertex is a graph whose vertice is a vertex whose deletion disconnects the graph. What do we see about that red vertex? Okay. The red vertex is a vertex whose deletion will disconnect the graph. Does everybody kind of see that? If I delete it, if I delete it, the blue nodes and the green nodes can't talk to each other anymore. Okay? Fair enough. Okay? So can anyone give me an algorithm? And I want, as ideally you should be, okay, sorry, let's try this. Can anyone give me an algorithm to tell whether a graph has an articulation vertex? A vertex whose deletion will disconnect the graph. I want a correct, even if slow one. How would you tell if the graph contains a vertex whose deletion will disconnect the graph? Any ideas?
I think it has to have exactly two edges with odd number of vertices, with exactly, maybe with odd number of vertices.
You're saying something having to do with an odd number of vertices or something like that? I'm not sure I understand that. I'm seeing something on the thing. A articulation vertex is a vertex whose deletion will disconnect the graph. What if we delete the vertex from try taking a graph, taking a vertex, deleting it, and ask whether the graph is connected? How do we delete a vertex from an adjacency list? What would be, if I wanted to delete a vertex from a graph, how would I do it?
Just take all of the vertices that it's connected to and set those to 0.
I basically take the edges adjacent to this vertex and delete them from the graph, right? So if I want to delete vertex X, I look at the adjacency list for X, and if there's vertices, Y and Z, I now go to the list Y, vertex list for Z, and delete the X from it, and I go to the list for Y and delete the X from it, and of course delete these things. So my claim is one way I could find a vertex whose deletion will disconnect the graph would be to, for I goes from 1 to n, take the ith vertex, delete it, do a depth first search of the rest of the graph, and see whether I visit every other vertex. If after I've deleted that vertex and I did a depth first search or a breadth first search, I would visit every vertex in that connected component. Does everybody kind of see that? Remember, depth first search, a breadth first search from one vertex will visit everything that's reachable from it. If I did a breadth first search or a depth first search from a graph where I deleted a vertex, either the remaining graph will have one component or it will have more than one component. If it has more than one component, the vertex I deleted had to be an articulation vertex, had to be a cut node. Otherwise, I will add that vertex back to the graph and then do another deletion of a vertex and a breadth first search. And my claim is that if I did n rounds of delete a vertex and do a BFS or a DFS, this will test every vertex whether it is an articulation vertex. And in sort of n times m plus n, I would find all the articulation vertices of the graph. How many people are with me on that? I'm not getting as much feedback as I'd like to get. Okay, what's the question? So you would have to count the total number of components beforehand. That's right. So I'm first going to do a component to tell whether it's connected. If the graph is already disconnected, then the theorist is happy. He can go home without blowing anything up because it's already disconnected, right? But otherwise, they will go and count, yeah, it's connected. I'm now going to go and delete a vertex and do a BFS, okay? And that will show it to me, okay? So everyone's saying, does everybody see this, that I could do this as a function of n different traversals? But there's a comment here that maybe this sounds slower. Do I have to do n different traversals? Or if I am very, very clever about what I do, might I be able to get away with one depth first traversal? And I want to say, let's think about what happens if we do one depth first traversal. What are the articulation vertices here? On this particular graph, what is an articulation vertex? Well, this one and this one are both articulation vertices. Okay. So is this one. If I delete this one, I will separate this chunk of it from the rest of the graph. If I delete this vertex, I will separate this chunk from the rest of the graph. If I delete this vertex, I will separate this chunk from the rest of the graph. Does everybody kind of see that? Does everybody agree these three vertices now are articulation vertices? Under what condition is a vertex going to be an articulation vertex? Well, we know that in a depth first search of a graph, everything is either a tree edge, okay, or a back edge, right? Under what condition won't deleting, if I delete that vertex, what has to happen in order for it not to disconnect the graph? Does everybody see that what I need is, the only way I can save it is with a back edge that jumps above me? The only way I am not an articulation vertex is if I have a descendant of mine who has a back edge to an ancestor bigger than me, older than me, a more proper ancestor. Does everybody kind of get that idea? Look at this one again, just to make sure we're seeing it. Okay. How can I make this node not be an articulation vertex? The only way that would happen is if there was one vertex in the lower component that had a back edge to a higher component, right? To a higher ancestor. Could I have saved it by going to a brother node like that? You're saying yes? Well, no. Okay, not to here. Okay, because this is a cross edge. This edge is not going to an ancestor, right? In a depth first search, I couldn't have an edge like that. But I can have an edge going back. If you want to say, why isn't, what has to be done to make this not be a cut node? Well, I've got to go from here to a proper ancestor of that node, somebody who's above it. Perhaps its parent or grandparent or something like that. It doesn't have to go to the root. Any questions? Does everybody see that this idea of an edge going back to a higher ancestor is what is necessary to keep the graph connected if we're deleting this guy? Any questions about that? Okay. I think of this as being, what would happen in a James Bond film? You have the bad guy is sitting here at the node. Okay? He's having his henchmen cut this node. Here's James Bond. Okay? He's sitting here on this graph that's kind of hanging down, right? The henchman is busy cutting this node, waiting for James Bond to fall to his death. What is the only way that James Bond gets out of this thing? You've seen the movie, okay? What would happen? He would grab a spear gun, which has some kind of a wire, a rope attached to it, a harpoon, and would go bunk, shoot that road up here. Now he's got a back edge. Now they cut this thing. The whole component is going to drop down. But because the back edge saves him and keeps him connected. And then he starts to climb up the rope and goes after the bad guy. Do people kind of see how this organization of the graph into tree edges and back edges is kind of what lets us see that kind of an idea? Any questions? The code is in the book, and I encourage you to try to take a look at that and to try to understand it as a more complicated depth first search algorithm. But any questions about finding a cut node in a graph and see that this really does it? Any questions? Okay. The second example of a depth first search algorithm that I want you to really, really understand, because it's even more important than finding cut nodes, is a problem on a directed graph called topological sorting. Topological sorting is the mother of all things to do on directed graphs, directed acyclic graph. What is a directed acyclic graph? It is a graph that is directed, the edges go one way, but it has no cycles in it, okay? And, a topological sort is an ordering of the vertices such that all the edges go from left to right. Maybe you couldn't have seen it before, but look, I just blew this thing up. Does everybody see that this is a directed graph? Every vertex edge goes in a particular way as by the arrows. Does it have any cycles to it? A cycle means I can go someplace and get back to where I was without violating any directions. I could go bunk, bunk, but now I'm trapped. I can't get back. I could go bunk, 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 but I can't go back. Does everybody see that if I have an ordering like this, the vertices G, A, B, C, F, E, D, all the edges, when I lay them out, all go from left to right. A directed acyclic graph or a DAG has a topological sort is kind of an ordering of the vertices from left to right such that all the edges go from left to right. Any questions? If a graph had a cycle in it, a directed cycle, could there be an ordering where all the edges go from left to right? I'm seeing no, a head shake. Why not? What's to stop me? Well, if I have a cycle, let's say I start my cycle from G, I go to A, maybe I go to C. If I have a cycle that goes back to G, it's got to go in the other direction, right? So only a graph that is a DAG, has no directed cycles, can have a left-right ordering. Now, it's very important to recognize that a lot of interesting graphs that you deal with are DAGs, okay? And the fact that they are directed acyclic graphs is necessary for you to be able to do something with it. For example, again, some of you guys may be staying home these days because of the COVID and staying here, and you're not leaving your house. Well, I get dressed every day, and I have decisions to make in order to do it. Why is that? Because I put on various garments. If I'm getting dressed up, I might wear all of these things. I'm going to claim that it's important that I put on certain items before other items. Is it clear that I have to put on my undershorts before I put on my pants? It would look very funny if I put on my pants after my undershort, my undershorts after my pants, right? You can imagine that every bit of clothing has certain priorities. I can't put on my shoes until I put on my socks. I can't put on my undershorts, my pants, until after I put on my undershort. I can't put on my shoes until after I have put my pants on. Okay? According to this, it says that I want to put my undershorts on before my shoes. I think that's good practice. Okay, we can argue whether that's really, really necessary. But does everybody get the idea that in the course of getting dressed in the morning, certain clothing, there's a relationship between certain pairs of things where you have to put one of them on before the other? What would happen if there were garments, clothing garments, where you had to put A on before B, and you had to put B on before C, and you had to put C on before A? Does everybody agree that if we had this, if we had a cycle, nobody could get dressed in the morning? What I need in order to decide how to get dressed is an ordering where I respect all of these precedence constraints. And I claim that there's a lot of them, because this could be one. What is one way to do it? I could put on my socks first, maybe then put on my shorts. Maybe then I could put on my watch. After I put on my watch, what can I do now? What's the next garment I can put on? If I have socks, shorts, and watch on, is there anything else I can put on?
Shirt.
Shirt? Let me put on a shirt. That's a nice thing. After I put on my shirt, what can I put on? Any idea? Is there anything I can put on?
Pants.
I can put on my pants, okay? So I'll put on my pants. What is the next thing I can put on? Anything else I can put on at this point, or am I stuck?
Belt.
Belt.
I can put on my belt. After I put on my belt, what can I put on?
A tie.
I could put on a tie. That would be nice, right? Okay. That I think is the seventh one. Once I finish my seventh thing, what can I put on now?
Jacket.
Jacket. And then what could I put on?
Shoes.
Shoes. Okay. Does everybody see that there's an order there? And there's lots of different orders. Okay. When, you could have done, could be many, many different topological sorts for a given DAG. And each one of them prescribes a reasonable schedule, a reasonable ordering for doing jobs. Any questions?
I have a question. Is there a way to sort of represent in that graph that after you put on a tie, directly after that, the next thing must be a jacket? Or is it...
Well, how could it be that that after I put on a tie, I must have, let's say that I had, sometimes there could be only one ordering. Suppose my DAG looked like this. Does everybody see this? Where this is a prerequisite to that, this is a prerequisite for this. In this DAG, I would have no choice but to do them in that fixed order, right? So sometimes the precedents are where I have a lot of choices. Sometimes I have no choices, or only one choice at every spot. Okay? Topological sort is finding and ordering for that. And realize that whenever you have in your life, you're going to see a directed acyclic graph come up in an application. The first thing I bet you're going to want to do is to topologically sort it. Do you guys have any directed acyclic graphs in your life? Okay, I know you get dressed in the morning, but what else is it? Package dependencies. Package dependencies are kind of interesting. I think what that means is you're telling me you've got some piece of code where this depends upon some other things that you have to do before it. And this depends on other things before that, right? There had better not be a cycle in your package dependencies, or else there's no way to compile the thing, right? Okay? So yes, that is a DAG. I see course scheduling. When you guys try to take, why are you taking 373 now? The reason presumably is you have taken 214 and the linear algebra class, so you had the prerequisites. Does everybody see that if we had these blocks represent courses, some courses are prerequisites for some other courses, right? So the prerequisite thing is a directed graph. Why do we, is the prerequisite schedule acyclic? What would happen if we insisted that in order to take CSE 373, you had to have first taken 214. Then after 214, you took 114. And then after 114, you had to take 215. What would happen if we had a cycle in the prerequisite? Well, we couldn't have CS majors, right? There was no way you could graduate, okay? So a lot of things in life are DAGs by definition. And finding the order to process these things is a topological sort. Any questions about that? Okay, topological sorting is one of the things that you have to carry away with you. Learn to recognize what in the world is a DAG, and recognize that doing a topological sort is a very healthy thing to want to do with it. Any questions? Let me show you two algorithms to find topological sorts. One of them is easy in the sense that if you really understand depth first search, well, it follows automatically, okay? We know that in a depth first search, okay, what do we know? Well, again, the layout of edges in, a DAG is a little bit different than an undirected graph. We can have edges go to cross edges. We can have forward edges, but if we have a DAG, we cannot have any back edges. Does everybody see that the back edge is what created the cycle? Okay. So what is the idea of doing topological sorting by depth first search? Well, we're basically going to do things that are conceptually making sure we don't find any back edges. If we don't have a back edge, okay, if we have a back edge, that is going to create a cycle. That was the idea of our cycle generation algorithm. So long as we avoid a back edge, we are going to have a a DAG. If we have a DAG, what is going to be interesting? If I'm doing my processing, I'm doing depth first search. Ooh, I visit this. I visit this. I have a child, I back up. Notice that this guy that's backing up has all of these guys as a ancestor, okay? That all of these guys are ancestors of this node that's backing up, right? That means that this guy has to be later on the topological sort than this one, and this one. So what is the idea? The moment we finish with a vertex, exploring all of its outgoing edges, we are going to push it on a stack, okay? And the claim is that if we take the edges, the vertices, in order of reverse order of finishing time, kabunk, 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 this vertex is finished, okay? If we have them in the order of finishing time, this will finish first, second, third, fourth. If we put them in reverse order of finishing time, that will create a topological order, okay? And I encourage you to go through that and figure that one out a little bit. I think I didn't really prove it to you, but it should be something that you start to see where it's coming from. By definition, if I have an edge from me to you, I had better be to the left of you, okay? And in particular, the observation is that when I do a depth first search from here, it's going to finish before I get another chance to start. So the finishing time of this vertex, if there is an edge from me to you, the finishing time of the traversal from here has got to be later, got to be earlier than the finishing time of this vertex. So if I put the vertices in reverse order of finishing time, I will get a topological sort. Any questions about that?
I just wanted to clarify one thing. If in a topological sort, if you can have a forward edge, then doesn't that mean that throughout some part of your traversal, you had to go back to that like root node or like?
What's going to happen on a depth first search of a directed graph, which we agree is a little bit of a trickier thing? What is a depth first search of a, sorry, let me come back to this a little bit. Let me erase this. What is going to happen if I have, what's going to happen in the finishing time if I have a forward edge? Let's look at what might happen. I start from this vertex. Ooh, I discover somebody. Ooh, I discover somebody. Ooh, I discover somebody. I look at the neighbors of this guy. I have no more neighbors. This guy is now finished at time 3. 1. It started at time 1. Started at time 2. Let's say this one started at time 0. 1, 2. This one started at time 3. It finished at time 4. Now I backtrack to this, excuse me. Now I backtrack here. There's no other nade. This guy's finished. I backtrack to this guy. Finishes. I backtrack to this guy. I look at its neighbors. There's no reason why this couldn't have a directed edge going forward, right? I didn't process this edge until you got back to me after I had explored these guys. So forward edges in a directed graph are perfectly kosher. Does everybody kind of see that? Okay. But in a cyclic graph, a back edge is suicide. It's no longer a, it can't happen because it would create a cycle. Any questions? Any questions about what a DAG is or an acyclic, an acyclic graph, a directed acyclic graph, and what a topological sort is, and why it might be an interesting thing, and why kind of the reverse of the finishing order of depth first search does it. Okay, I think that was a fair amount of material. I'm going to stop here. I do encourage you to look at the notes and look at the section in the book carefully to make sure that this is going to be okay. Okay? Any questions?
Yes, can you explain one more time why we take the finishing times in reverse?
Why do we take the finishing time in inverse? Notice that when you're doing a depth first search, what is happening? This is a question of making sure you understand the mechanics of what a depth first search is doing. You're starting from a node, and the moment you discover somebody else, you are pushed on the stack. And we now work from the new node, right? You may have other edges coming out of you, but we're not going to explore them until we have completely explored everything reachable from the first, your first child, right? So this is going to go do its thing, do its thing. It's going to backtrack, backtrack, backtrack. Now, once I've explored everything reachable from here, this guy is now finished, right? And only after finishing this guy do I get to resume my search through some of my other edges, right? So this node has to finish first rather than this one. But if I have an edge like this, if this finishes at time 36, and this finishes later, it might finish at time 56. Note that I want this node with the earlier finishing time to be the right of the node that finished later, which means I want them in the reverse order of finishing time. Any questions about that? Does that answer it?
Yes, thank you.
Okay. Any other questions? If not, take a look at this. This requires quiet contemplation to really understand it. So this weekend, I encourage you to do some quiet contemplation, and we will discuss it then. Okay? Anything else?